Hello everybody and welcome to the math skills lesson on units. Now in physics we use units on the end of every measurement we make. The reason why we do this is mainly as a communication tool. If we've got a number written down without a unit, it's very difficult to tell what that number relates to. However, if we've got a unit on the end of it, then we know exactly what it means. We know if it's got meters, say, that it's a measurement of length. Now at GCSE you would have come across a lot of different units. What I suggest you do is pause this video just for a moment and see if you can very quickly write down, even if it's just the symbols of them, some of the units that you can remember from GCSE, and then once you've done that, come back and we'll talk about them more. So let's have a look at some of the common ones that you would have come across at GCSE. Now already in the introduction I mentioned the metre, which of course is the measurement of length. Hopefully at the same time you thought about the second, which is of course the measurement of time, and then potentially you may have even gone on to say metres per second as the unit of velocity. Other common ones that we use, joules being the unit of energy and newtons being the unit of force, again are very common when we look at GCSE. Kilograms as well, the unit of mass, and then when we get into electricity we have the amp, the unit of current, we have the volt, the unit of potential difference, and the ohm, which is the unit of resistance. Now of course there are many more units than that. We're not going to go into listing all of them because that would make for one extremely boring video. The system of units that we use though is known as the SI system. So these are all classed as SI units. And the reason why it's called SI stands for International System, but of course you can see the French just below there. I'm not going to attempt to say it in French because it's been an extremely long time since I spoke French in anger. But the system is governed by the French. You can go to the Bureau of Units and Weights and Measures in Paris if you really want to. It was all born really out of post-French Revolution when they tried to move everything across to a decimal system. In other words, where everything was based on the number 10. It worked for the vast majority of things that we now use in everyday life. The French did try to do it with time and have decimal time, but it didn't quite work. The rest of them though, and the rest of the units that the French invented at that time have stuck and are now used in physics and in general in the world in order to do our measurements and our weights and all that kind of stuff. Now you'll have noticed that I've separated the units that I've mentioned so far into two columns, and the reason why I've done that is because we've got two different types of SI units. We have base units and we have derived units. Firstly then we will look at the base units. Now there are 7 base units. Firstly then I will give you the symbol of all 7 of them. We have S, we have M, we have kg, we have capital A, we have capital K, we have MOL, and we have CD. Now at this point you may or may not recognise some or potentially all of those. Again, what I suggest you do is just pause the video and see if you can work out what the names of all of these are and see if you can remember from GCSE what their quantity is, in other words what they measure. So hopefully the top 3 at least will be relatively easy. Lowercase s, the name for that is the second, and that of course is to measure time. Lowercase m is the metre and is to measure distance, and kg is the kilogram and measures mass. So those three are probably the most common of the base units that you will have used at GCSE, and obviously at A level we're going to see them quite a lot as well. Now hopefully the next one you'll recognise as well. It's known as the ampere, and it measures current. More specifically, it measures electric current. Now K you may or may not have seen before. Some of you may recognise it. It is the Kelvin and is the measure of temperature. The sixth one, MOL, is the mole. Now you hopefully should have seen that in chemistry lessons. You'll see, use it in chemistry quite a lot. It's the measure of the amount of substance. Now, to be honest, the last one I would be highly surprised if you did manage to get this. It's known as the candela, and it is the measurement, the quantity is for luminous intensity. In other words, it's how much light something is emitting. As I said, though, I will be highly surprised if you got candela, because to be honest, we didn't use it at all at GCSE, and we don't even use it at A level. And to be brutally honest, even through my degree, I never actually used candela properly as a unit. So we aren't going to come across it again over the next couple of years at A level. But of course, I'm going to tell you about it anyway, just so you've got the complete picture. Now, the reason why these seven are defined as the base units is because every single one of them, so all seven of them, are defined based on some fundamental constant of nature. The metre, for example, is actually defined from the speed of light, which we know obviously as a value is close to 3 times 10 to the 8 metres per second. And as I said, the metre is defined based on that constant, which of course is a fundamental constant of nature. We know it's a constant and we know that it can't change. The ampere, for example, is based off the charge of an electron. And all the rest of them, as I said, are based off these fundamental constants of nature. All of the other units that we use, so the ones that we mentioned on the last screen, and obviously many more that you'll come across over the next couple of years at A level, are based on these base units, and these base units will make up those derived units. In other words, the derived units are derived from the base units. So now let's have a look at the derived units and how we can take the base units and we can derive these derived units from them. Now, possibly the easiest example we can look at is meters per second, which is of course the unit of speed or velocity, depending on whether you want to use the scalar version or the vector version. Now, when we look at the equation for speed or for velocity, let's just do it from a speed point of view. We know the classic equation, which is speed is equal to distance over time. Now, in maths, we place a lot of time and effort understanding what this symbol here means. Now, we know what the name of it is. The name of it is equals, but we really need to understand what it means. Now, in maths, what you're taught is that whatever is on this side of the equation must be exactly the same as what is on this side of the equation. So in maths, you might say that 8 is equal to 16 divided by 2. And that's perfectly valid because 8 on the left hand side, and when you do the calculation you've got 8 on the right hand side as well. Therefore the equal sign is perfectly valid. On each side of the equation we've got exactly the same thing. Now, of course, this works for units as well. If we go back to the equation and start to look at the units, well, we know that the unit of distance is metres, and we know that the unit of time is seconds. So on the right hand side we have the unit metres divided by seconds. Now, instead of saying metres divided by seconds every time, we instead use the word per. So we now have metres per second. Now, of course, you'll notice that the way I've written the units in green, and some of you at GCSE may have written the units like that, m/seconds. It's completely different to how I originally wrote the unit just up here in the top left hand corner. This is now where we have to start to get the A-level conventions into our head. Let me just remind you from maths, we know that if we write 1 over x, so the inverse of x, another way that we can write that using powers is x to the power of -1. Now, when we come back to metres per second, we can also write metres divided by seconds as metres multiplied by 1 over seconds. And then, of course, because of what we said earlier, that 1 over x is the same as writing x to the -1, we can now rewrite that as m multiplied by s to the -1. And of course, in physics, a lot of the time we tend to drop the multiplication symbol, and what we're left with for metres per second is therefore ms to the -1. Now, this style of notation using powers, negative powers, is the convention that is used mostly in physics. If you did get used to using this kind of notation at GCSE, unfortunately you will have to work to get that out of your brain and to learn this sort of more conventional way of writing the units. But again, that will come with practice, and you will soon get used to it as well. Now, of course, metres per second is an extremely simple example in the grand scheme of things. We can look at other units, other derived units as well. And one of the most common ones that we use in physics, especially when it comes to mechanics, is the Newton, capital N, which of course is the measure of force. Now, you'll notice that we do have some units which are capitalised and some units which are lowercased. In general, if they are capitalised, like the Newton, then they are named after a person, named after normally an historical scientist. So obviously the Newton is capitalised because it's named after Sir Isaac Newton, who's basically the father of physics in a lot of ways. Now, one of the skills that we need to develop is knowing how to take these derived units and how to work out what their base unit equivalents are. And let me show you how to do that using the Newton as an example. Now, the first thing we need to do is to think of an equation which has that unit contained in it. So we're looking for an equation where force is involved. Now, the first one that at least comes to my mind is Newton's second law, or at least the simplified version of Newton's second law, which is F is equal to ma. Force is equal to mass times acceleration. Now, remember what we said about the equal sign before. Whatever we've got on the left hand side, we must also have on the right hand side. So on the left hand side we have newtons. The unit of force is the Newton. And on the right hand side, well, Newton must be, and I'm going to put a triple equals here, which means equivalent to, again, more convention and an extra symbol for you to get your heads around. If we have a look at this then, well, mass is kilograms. Well, that's already a base unit, so that's brilliant. And then acceleration, well, again, hopefully from GCSE you will remember that the unit for acceleration is meters per second squared. Notice the use of units here. It's not m/s squared. Okay, so we're not using that anymore, which you may have seen and used a lot at GCSE. Unfortunately, that way of doing it we can't use anymore. So ms to the minus 2. But of course, meters per second squared is the unit for acceleration. So there we go, very easily, just using one equation, we've taken the Newton, which is the derived unit, and we've worked out, we've gone back to the base units and seen what the equivalent in base units is. So the Newton is equivalent to kilogram meters per second squared. Before we move on, let me just give you one further example so that we can see further how we do it. And let's now have a look at this unit, which again I hope you recognise is the joule. Again capitalised because it's named after somebody, and that is the unit of energy. Now again, in order to break this back down, in order to go back down to the base units, we need to think of an equation that uses joules. Now there are probably a couple that come to mind at this point. The first one I'm going to do is W is equal to Fs. Work done is equal to force times distance. So let's now start to look at the units. Well, we know that the unit of work done is joules, and that will be equivalent to, well, the unit of force is newtons, and the unit of distance is meters. Now we're not quite there, because while meters is a base unit, obviously the Newton, as we've just seen, is a derived unit. But fortunately we don't have to go all the way back through, because on the left hand side of the screen we've got the equivalent of the Newton. So we can now say the joule is the equivalent to kilogram meters per second squared, so that's from the Newton. And then obviously we need to multiply that by meters from the distance. Just to finally tidy it up, then we have meters and meters. So we have meters times meters, which makes meters squared. So finally we can say joule is equivalent to kilogram meters squared per second squared. Now, of course, I chose work done is force times distance. I'm guessing that's probably not the first equation for many of you that came to mind. Let me just get rid of that bit there. Normally, when we talk about joules, you will think of energy straight away. And it's likely that you will have thought of either the kinetic energy equation or the gravitational potential energy equation first. Let's use the kinetic energy equation. EK is equal to a half mv squared. And let's go through that same process again. Now, kinetic energy is an energy and is therefore joules. When we look at this, the half doesn't have a unit because it is just a number. It is therefore dimensionless, so we can ignore it. For meters, we know that we have kilograms. And then for velocity, we have, as we saw on the last slide, meters per second. But of course, it's velocity squared, and therefore we have to square the unit as well. When we square that unit, we obviously leave the kilograms alone, and we square both of the things inside the brackets, so we end up with meters squared. We start with per second, and therefore we end up with per second squared. And hopefully, unsurprisingly, you can see that we've used a different equation for energy, but we've ended up with exactly the same answer as we did before. So now it's time for you to have a go at this. I'm going to give you two units. I'm going to give you first the watt, which is the unit of power, and then I'm going to give you the volt, which is the unit of potential difference. So what I'd like you to do at this point is to pause the video and to have a go to see if you can break these two units down, these two derived units, down into their base equivalents. As I said, pause the video, have a go, and come back once you think you've got an answer. So let's have a look at the watt first. Now the watt, as we said, is the unit of power. There are a couple of different equations that you could use for this. The best equation though to use is power is equal to energy divided by time. Now when we break this down and have a look at the units, we have watts on the left hand side, and that is equivalent to joules, that's the unit of energy, divided by seconds, that's the unit of time, and so remember that we're going to write therefore joules per second. Now we're happy with the seconds bit, that is a base unit, but as we saw on the last slide, joules is a derived unit, so we need to break that one down as well. Now fortunately we already know what joules is. That is kilogram metre squared per second squared. That's the joule. Don't forget that we then need to multiply again by seconds to the -1. So we're almost there. All of these, kilogram, metre and second, are all base units. But of course here we have per second squared and per second. What we're left with then is that watts is equivalent to kilogram metre squared per second cubed. Now for the volt, again there are a couple of different ways that we can go here. Possibly the easiest way to go, especially now that we've calculated or worked out what the equivalent of the watt is probably to go for the equation P is equal to IV. Now because we're looking at the volt, I want to rearrange this equation first to make potential difference the subject of the equation, and therefore V is equal to P over I. Now we can start to look at the units. Well, the volt is equivalent to watts on the top divided by, well, the unit of current is amps, so it becomes watts per amp. We've obviously just now looked at the equivalent of the watt, so we can plug that in, kilogram metres squared per second cubed, and then we have per amp as well. So the equivalent of the volt is kilogram metres squared per second cubed per amp. Now of course you may have gone a slightly different way with that. An alternative route to the base unit equivalent of the volt is to use the equation E is equal to QV, so energy is equal to charge multiplied by potential difference. Once again we rearrange the equation. V is equal to E over Q, and we can say that the volt is the equivalent to joules for energy, and then coulombs is charge, and we divide it by, so it ends up as per coulomb. Now we've got the base equivalent of joules already, kilogram metre squared per second squared. What about coulombs? We do need to break that one down a little bit further as well. Now in order to do that, we come in green up here, we can use the equation Q is equal to IT, and therefore we can say that the coulomb is equivalent to amps for current and seconds for time, and there we go. So we've got a bonus unit in there as well. We can see that the coulomb is equivalent to amp seconds. When we come back over to the volt then, well, joules, once again, we know, and we've seen a couple of times before now, is kilogram metre squared per second squared. And we're now going to divide that by the unit for coulombs. Now, when we divide it, we need to put a -1 on both the amp bit and the second bit. So we end up with per amp and per second. Once again, we've got per second squared and per second, so when we tidy that up, hopefully unsurprisingly now, we end up with kilogram metre squared per second cubed per amp. So to summarise, in this lesson we've looked at the system of units known as the SI units that we use in physics. They're split down into two types, the base units and the derived units. The base units are the second, the metre, the kilogram, amps, Kelvin, mole and candela. And those 7 units are all defined by fundamental constants of nature. All the other units that we're going to use in physics are known as derived units, and in order to go back and look at the base equivalent of a derived unit, what we need to do is think of an equation and remember that your units must be the same on the left hand side of the equation and the right hand side of the equation. So that's it for this lesson. If there are any questions, please let me know.